I apologize for having this in two recordings. I accidentally hit stop instead of pause. I'll link the two together. I'll put a link in the notes for each one of the videos so you don't have to look for them. So where we were when I clicked that was spatial distortion. So spatial distortion is caused by the thickness of the patient, the object, and also the depth within the object, but also the divergent central ray or angulation. So where I was going before I clicked stop instead of pause was where I've seen the perception of magnification be an issue. It was actually the perception was exactly backwards, was with a abdominal aortic aneurysm, which is what we're looking at here. So the spine, the aorta runs directly anterior to the spine, and then this area of calcification here is your aneurysm. So an aneurysm is just a bulging in an artery, and the body tries to protect itself by putting calcium into the stretched out portion of the artery. That's all the aneurysm is a big artery. And the calcium provides some degree of stability. So we should not see the aorta on a KUB, but we do here because the aneurysm is stretched out. So you might look at this and say, well, you know, the reason that it appears so large is because it's anterior to the spine. We have an increase in OID, and you would be accurate. So it's probably not as dramatic as what it looks like. It's still serious. This is not a patient that you would want to inject with 100 cc's of contrast and do an IVP on the patient. They would need to do a CAT scan and assess how big that aneurysm is, because it's a little bit deceptive because of the increase in OID. So where are we? So that would be your spatial distortion. So is distortion the same across the image? It depends on if we have magnification, size distortion, or shape distortion. If we have shape distortion, no, we have unequal magnification. Distortion the same as throughout the anatomical thicknesses, and again, that would be no. We just took a look at that. We've got spatial distortion that can obscure that a little bit. So focal spot blur occurs because we create X-rays on an area on the anode, not a pinpoint source. So remember your line focus principle. We've got an actual focal spot, and that's the actual area of bombardment on the anode where the electrons traveling from cathode impact. That's an actual focal spot. But because of the angulation of the anode, we get a smaller projected focal spot, and that's your effective focal spot. We get a smaller effective focal spot than the actual focal spot, but it's still over a large area, relatively large area. So we get blur because it's not from a point source. So we looked at the effects of the focal spot blur as it comes off of the anode. As X-ray beam comes off of the anode, we create X-rays, and they're isotropic. As they leave the anode, they are projected with equal intensity in all different directions, and that's isotropic emissions. And if we have some X-rays that are created here, they'll escape this end of the X-ray tube, interact with the edge of the object that we're interested in seeing. We'll also have some that come from down here. So they cross over at the point of the object, and the crossover in the distance between the object and the image receptor is what gives us our blur. So as we increase our OID, then we get an increase in blur. As we increase our focal spot size, we get an increase in blur. but the blur is always worse at the cathode end of the X-ray tube than what it is at the anode end of the X-ray tube. So why does it occur? Well, it occurs because we create from an area and not a point. Focal spot blur decreases spatial resolution, sharpness for recorded detail, spatial resolution, or resolution or sharpness. All of that means the same thing. It decreases. It's calculated, again, on page 286 of Bushong. You've got a couple of different ways to calculate. SOD over OID. Remember, your first step there is to subtract OID from SID to get your SOD. That's SOD over SID is equal to effective focal spot over focal spot blur. So remember, you'll always get at least 3, or you'll always get all but one of the factors. So most likely what you're not going to get there is focal spot blur. Or if you want to simplify it a little bit, you can go focal spot blur is equal to effective focal spot times OID over SOD. Just remove the cross multiplication. All right, so the blur is not the same on both ends. Remember, it's worse on the cathode end of the X-ray tube. So don't confuse the difference in focal spot blur with your anode heel effect. The anode heel effect is the intensity difference between the cathode and anode into the X-ray tube. So the heel effect looks like this, and we talked about this in class today. The intensity difference between cathode and anode into the X-ray tube, because the absorption characteristics of the anode, they've got it drawn out here. We've got some filtration effects of the anode itself. We're going to have fewer X-rays emitted on the anode end of the X-ray tube than what we will on the cathode. So we have an increase in intensity. It's relative intensity. We have an increase in intensity on the cathode side of the X-ray tube as opposed to the anode side of the X-ray tube. So the middle of our X-ray beam represents 100% of the intensity that we want. Intensity increases on the cathode side, decreases on the anode side. So that's not to be confused with the difference in focal spot blur. So focal spot blur increases on the cathode side of the X-ray tube and decreases on the anode side of the X-ray tube. Intensity, hang on, let me get back to it. Intensity increases on the cathode side, decreases on the anode side. All right, so what causes it? That would be the filtration effects of the anode itself. What are the imaging implications? You put your thicker anatomy towards the cathode side of the X-ray tube. If you don't, then theoretically you could have an increase in exposure on the cathode side than on the anode side. So you put your thicker anatomy on the cathode side. So we have two different types of motion. We've got voluntary and involuntary motion. So what that leads to is loss of sharpness, recorded detail, and blur on the image. Best way to limit voluntary motion is with good instructions. And try not to get too philosophical about the difference between voluntary motion and involuntary motion. Just stick with the textbook definitions. Can the patient prevent the motion? If so, that's voluntary motion. If not, that's involuntary motion. So heartbeat, bowels, things like that would be involuntary motion. Well, what about kids? They can hold their breath, they just won't. Well, we're going to count that as involuntary motion then. So voluntary motion, the best way to control voluntary motion, good instructions. Involuntary motion is a decrease in exposure time. So using your reciprocity again, increase MA, decrease time. We talked in class today, what if you're on working with an imaging system that has limited options if you're working portables? How can you decrease your time? Well, then you would have to increase your KVP. If you are phototiming, you can increase your KVP. And again, normally we want to change our mass for things that we don't need to change our differential absorption for. But since KVP really doesn't affect contrast the way it used to, there's no reason that you can't use KVP to control motion as well. The one downside, and again this is theoretical because you may never see it, is that if you increase your KVP and that pushes your time down low enough, you very well may introduce quantum model because your exposure gets so low. So what can we do to ensure the highest spatial resolution? Positioning wise, we want to do those things that would prevent us from having either type of distortion. So we want to use an adequate SID. We want to use as low of OID as possible. We would want to have our anatomy parallel to the image receptor and perpendicular to the central ray, with our image receptor perpendicular to the central ray. So all of that stuff. We want to center on the object of interest as well. Collimation we talked about in class, and that's a digital thing. So if you don't collimate, then you get that minimized image. So that's not really magnification of the image, it's magnification of the display. It's not really the same thing, but it has the same net effect. You're going to have a little bitty image. Image receptors really doesn't play a part anymore. Computer algorithm really doesn't play a part in your spatial resolution, but it does in contrast resolution. Use proper technical factors and certainly as low an OID as possible. So what I would recommend that you do is make sure that you look through your DeAngelis. Some of the questions are coming from DeAngelis. Look through your review from the last test, because some of the stuff will be from the last test will be on this test as well. Make sure you go through your textbook.